Okay, so now we're going to talk about real gases. So we return to ideal gas. And if it's an ideal gas, the left hand should equal the right hand, hence the equal sign. So if I were to take PV divided by nRT, I should get 1. 1 would help. Well, if I don't get 1, however, if PV over nRT is greater than 1, or if PV over nRT is less than 1, I can learn a lot about my system. And so if we look at the ratios of these, I can learn whether or not nRT is less than PV or if nRT is greater than pressure volume. And one of the cool things, so by the way, so we call this relationship, so equals 1 if ideal. And so these would then be considered non-ideal gases. And this ratio is called the compression factor. Compression factor. Compression factor. So Z is equal to PV over RTN, and I'm going to do a quick combination. Okay, so V sub M is known as our molar volume. So if I had 1 mole of a stuff, then what's its volume? That would be my molar volume. So you'll see several throughout the course, V sub M will pop up most of the time because we don't really care if you have a lot of our little stuff. So the N is kind of annoying. Anyway, so this becomes PVM over RT, compression factor. So now I'm going to show you, share screen, really cool plot where we're going to look at the compression factor as a function of pressure, and you're going to see it change for various types of gases. Go team, push the button, share, ta-da. Okay, so non-ideality measured through the compression factor Z. Here's a plot. Now let's look at the axes real quick. You've got compression factor Z on the y-axis, and then on the x-axis, we've got pressure in atmospheres. Very important to always note the scale, 0 to about 500 atmospheres. Okay, more on that in a second. So first, we'll just look at it for a second. We know that if ideal gas law, or sorry, if the gas behaves ideally, Z equals 1, groovy. So if at any of these pressures we find ourselves on this value, that means the gas behaves ideally. So for nitrogen, you've got this red dash line. Hydrogen is this one. This is methane. Here's helium. Then you've got CO2 over here. 2 of these are not like the others. So you can see that depending on the chemical character, these aren't just point particles now. As you start to get into real gases as well, as you get into non-theoretical gases or non-theoretical systems, the chemistry is going to start to play a role. And so as we increase pressure, look at how the ratio of PV to nRT changes. So N2 and helium, both beautifully linear. That's kind of fun. And so this linearity tells us something, but also it's above 1. Cool? So gases are ideal if they equal 1. If they're above 1, however, it's less compressible than predicted by the ideal gas equation. Less compressible means that nRT is going to be smaller than pressure times volume. If it's less compressible and you change the pressure, you're not going to be able to change the pressure of the gas as much. And so what that causes then is you can't smash them together. Methane, however, or CO2 for that matter, gloriously smash them together. So, and I say smash them together, I mean the gas becomes more compressible. So as you compress the gas, it becomes capable of pushing it in. Imagine this is like silly putty. So, you push silly putty or some sort of dough like stuff, you can push it in, it's very compressible. A block of lead, not so compressible. So that compression can tell us about the intermolecular interactions that are going on. Other thing to note, one of the things about physical chemistry is looking at an answer or looking at a value and giving it reasonable meaning. Okay, so I would tell you, oh, I have CO2 in my beer, hooray. I wish I had a beer right now. But if I take it to 200 atmospheres, the gas itself of the CO2 is going to change. It's no longer going to behave ideally. Well, what is 200 atmospheres? So I did the calculation. Oh, actually, I did the calculation for 100 atmospheres. Okay, so in my beers, we've got 100 atmospheres. So 1 atmosphere, way over here, down about right there or so, where pretty much everything behaves ideally. Think about why I can say that statement. Everything behaves ideally around 1 atmosphere. It's about 14 psi, 14 pounds per square inch. So for 100 atmospheres, where, let's see, who's that? Hydrogen does some wonky stuff, and transitions from a compressible gas to a non-compressible gas at about 100 atmospheres, that's 1,400 pounds per square inch. 1,400 pounds per square inch. Cool? What is that? That's like a cow on a quarter. Like if you put an entire cow and have it like balance on a quarter, the weight under that quarter, the pressure under that quarter, about a square inch, is 100 atmospheres. These are ridiculous pressures. And just for fun, 500 is about 7,000 psi, 7,000 pounds per square inch. That's a lot of pounds. That's like half an elephant. Okay, so ridiculous pressures. But what happens at low pressure? All of those gases, regardless if they're compressible or not, if they react, well, they wouldn't react, but if they interact or not, they all behave ideally as P goes to 0. So as P gets smaller and smaller, as P goes this way, the limit, think calculus now. This is, by the way, a calculus class. It's a chemistry, it's calculus and chemistry. Anyway, but the limit, as P goes to 0, you have ideal behavior. And think about what that means. Here, I'm going to stop share. Where the hell's the stop share button? There it is. So as P goes to 0, so if I'm pushing, oh, this is going to be fun. Normally I'd be pushing on the board, but since there's a camera, this is going to be awesome. So I'm pushing on the camera, right? A lot of force, a lot of pressure, force per unit area. If I kind of ease back a bit and I don't have much pressure at all, much force, it's almost as if I'm not even there, right? So there's no interaction, okay? High pressure, not much pressure. As I get to the limit of 0 pressure, I'm practically not interacting with anything. And if I'm just a free float molecule all by my lonesome, I can behave as the way I would without any interference whatsoever. I would behave as an ideal gas. So regardless, nitrogen, hydrogen, CO2, methane, big ones, benzene, those are going to behave ideally as you get to 0 pressure. And that's why we call it a limiting law, because as the limit as P goes to 0, yields ideality, ideal gas behavior. Go team. Okay, what's next on the slide?